let's jump ahead and look at this heading, defining the number e. Now you've got this on your calculator. Maybe you've noticed. Let's see, this little tiny e is right above your division sign. You may not be able to see it on my screen. If you hit second divide, wait, sorry, I'm totally wrong. It's right above your LN button. There's an e to the x. Okay, this little e value. That's what we're going to talk about. And so what is this e? It actually has a lot to do when we start getting into exponential and later into logarithmic functions. So the way we define this number e, you think of e as something like pi. You know, pi is 3.141 and so on, right? It's that irrational number that never repeats, never ends. E is the same sort of idea. It's an irrational number. The decimal values continue. There's no pattern to it. And the way that we define that, it's 1 plus 1 over n to the nth power as n gets larger and larger, as n approaches infinity. So, you know, if you plug a large value of n into that function, then you get this value e. I know that sounds really strange, like you're probably wondering, why are we even talking about this, like 1 plus 1 over n to the nth power. But it turns out this number e, turns out it turns up in a lot of places in nature. If you look at things like exponential growth, it's a really useful number when you start trying to do modeling of, you know, different exponential functions and logarithmic functions in nature and just in the world and the way math works in the world. And so just know that it's a useful number for us as we do a lot of different, you know, models and things that try to describe the way that math is working in population growth and a lot of different things like that. And so 2.718281827, again, that's still an approximation. If you hit it on your calculator, e to the first power, you can see that yeah, there's that value 2.718281828. And again, there's not a pattern there. You can look it up on Google, Google e, and you'll see, find a page somewhere that lists probably thousands of decimal values for this number. And you can hit second divide and get that e. Thought I was mistaken earlier, but it's there. All right, so let's jump ahead and look at solving exponential equations. This is really where a lot of your homework comes from, is solving exponential equations. There's a really simple property we use to solve these equations. It says if a to the u equals a to the v, then u equals v. Now think about what that says. If two exponential expressions, a to the u, a to the v, if they're the same, then u has got to equal v, right? If the bases match, a to some power equals a to the some power, they're the same, those powers have to be the same. So a to the u equals a to the v means u equals v. So in other words, if we have like 2 to the x equals 2 to the fourth, those bases match, then we can say that x equals 4, right? That's what that property says. If the bases match, the exponents match. So how do we use that to solve an equation like example 4? 3 to the x plus 1 equals 81. Okay, well, the key to this, again, is that the bases have to match. Now, right now, the bases here don't match. This is a base of 3. This is a base of 81. But we can rewrite this. 81 is the same as 3 to the fourth power. You can check that on your calculator. We can rewrite 81 as a power of 3. And so now those bases match. So from that, we should get that x plus 1 equals 4. Well, if x plus 1 is 4, doesn't take much work to see that x is 3. In fact, you can check that. If you plug in a 3 there, 3 plus 1 is 4. 3 to the 4th does equal 81. So it checks. And that's the basic idea. Really the trickiest part of these problems is usually just trying to get those bases to match up. Once you get the bases to match, you just set the exponents equal to each other, and from there solve the equation that you've got. So let's look at the next example. E to the negative x squared equals a bunch of stuff. E to the x squared times 1 over e cubed. Now here's where we need to get into some of those properties of exponents, because again, this needs to ideally be written as e to some power equals e to some power, right? That's kind of the form we want. Now remember what e is. It's not a variable, it's a constant, right? That's 2.718, that value that we just mentioned. And so to use our properties of exponents, this left side is already written as e to the negative x squared. That's totally fine. Nothing wrong with that. It's e to a power. Over here, using some properties of exponents, we can write that as e to the 2x, multiply those powers, and then multiplying those together, we can just say e to the 2x over e cubed. And then since those bases match, we can subtract the exponents. Now if what I just did, those steps right here, rewriting that are unfamiliar, you need to go back and review your properties of exponents, okay? Because that's what we're using there. All right, so if you'll notice, I've got e raised to a power here, e raised to a power here. We've got basically this form, and so we can rewrite this, set the exponents equal to each other. And then from that, we need to solve that equation. Now here, this is it's a quadratic equation, right? We've got the x squared, so let's get all the terms on one side, add x squared to both sides. We get x squared plus 2x minus 3. And then we can solve this by factoring. Two numbers that multiply to negative 3 and add to 2. Just like that. And then set these equal to 0. If you think back to the last chapter, you could also say, what are the zeros here? If you remember that. X plus 3, x minus 1. The zeros are, whoops, that should be getting ahead of myself. Negative 3 and positive 1. So there's our solutions to our equation right there. Two solutions. Okay, I'm going to drop in another example here. This one's one that was in the book. I didn't get it in the notes, but we can drop it in here, no problem. So let's 4 to the 2x minus 1 equals 8 to the x plus 3. Alright, so working this out, again, those two sides need to be powers of the same base. So can we rewrite 8 as a power of 4? We really can't do that, right? 4 squared is 16. That's already, 8 is less than 16, so this just doesn't work out, right? We can't do that. So we can't rewrite the 8 as a power of 4. So maybe we can rewrite them both as some smaller power. So if you think about it, what's 4 and 8? Those are both powers of 2, right? 2 squared is 4. 2 cubed is 8. So we rewrite this and we say, all right, this is going to be 4 is the same as 2 squared. Still has that exponent, 2x minus 1. 8 is the same as 2 to the third power times x plus 3. So now we're getting closer. We got both of those bases to be 2's. Using a property of exponents here, we can really essentially distribute that 3 and that 2 into both of those exponents. So we get 2, and then that's going to be a 4x minus 2. Then that's 3x plus 9. Notice we've got both bases are 2's. So let's get those exponents and set them equal to each other. From there we solve this thing, subtract 3x from both sides. Add 2, we get 11. And there it is. And this is something you can check for a lot of these. If we want to check this, that says cheek. That doesn't say check. Just plug it back in, right? 2 times 11 minus 1, 11 plus 3. Hopefully this works. 22 minus 1 and 8 to the 14th. So 4 to the 21 equals 8 to the 14th. Well, let's pull out the calculator there because I don't know what 4 to the 21 power is, but my calculator can tell me. Okay. Now, what does that say? Looks like a decimal value, but it's really not. This is it's actually in scientific notation. Okay. That e, this is the same as saying 4.398 times 10 to the 12th. So if you think back to your science classes, scientific notation. And the best way to kind of handle this, okay, 4 to the 21 is that. What's 8 to the 14th? Those look to be the same, right? So yeah, those are both equal. Those are good. So it checks out. No problem. Okay, we've got another example here. It says many applications involve the exponential function. So here's an example of in statistics where we can use the exponential function to model a situation. It says between 9 and 10 p.m. cars arrive at Burger King's drive-thru at a rate of 12 cars per hour, or 0.2 cars per minute. Seems reasonable. Okay. The following formula from statistics can be used to determine the probability that a car will arrive within t minutes of 9 p.m. Now, what does that say? Let's decode that sentence. So this formula, this guy right here, tells us the probability or the chance of a car arriving within so many minutes of 9 p.m. So we plug in a number of minutes for t, and it tells us a probability, a percentage, a chance that a car will arrive within that many minutes of 9. So to make it make a little more sense, part A, determine the probability that a car will arrive within 5 minutes of 9 p.m. So that is before 9:05 p.m. What are the odds that a car arrives in the first 5 minutes there? So here t is equal to 5. So f of 5 is 1 minus e to the negative 0.2 t. And t here, let me back up, t is 5. Now you can punch all this in the calculator if you wish. It's not a bad idea though to say, all right, 0.2 times 5. We can do some simplifying here. Is 1, right? So this is 1 minus e to the negative 1. And so punching that in the calculator, it's not too bad. 1 minus e to a power, again, second ln. And then punch in negative 1. We get 0.632. Now again, that's a probability. So what that means, a probability is essentially a percentage, or we could say or 63.2%. So we're saying that the odds are 63.2% chance that a car arrives in the first 5 minutes. Okay. All right, seems pretty reasonable. If there's 12 cars per hour, there's a pretty decent chance a car is going to arrive in the first 5 minutes. Let's look at the next part here. Determine the probability that a car will arrive within 30 minutes of 9 p.m. Now, if you just think about this, what answer would we expect there? 12 cars per hour arrive, and we sit there for half an hour. We would expect that at least one car is going to show within that first half hour, right? If it's 12 cars per hour. And so if we plug in, again here, 30 minutes f of 30 is 1 minus e to the negative 0.2 times 30. You can run that through your calculator. You're going to get 1 minus e to the negative 6. And we can easily just use our last calculation, change the negative 1 to a negative 6. We get 0.998. Or 99.8%. So there's a really good chance that a car is going to arrive within half an hour. Now notice it's not a guaranteed chance, so there's still that 0.2% chance that maybe for some reason a car doesn't come. You know, maybe all the 12 cars arrive in that last half hour. Could be a ball game lets out or something, and you know, by 9:30 all of a sudden there's a big rush and a dozen cars come in the next half hour, after none being there the first half hour. You know, who knows what the situation is, but there is a chance that maybe a car doesn't show in the first half hour, but 99.8% chance that there will be a car. So that's just one example of an exponential function that models situation in statistics. So again, there's a lot of different situations we could use these, and if you get into statistics or you know, some other a lot of science models use these exponential functions. So but that's really it for the section. Biggest thing is solving those equations that we looked at. So if you have any questions, please let me know.